A comma B. These are the components of the vector. So this is how we draw the vector, always from the origin. Okay, we use those components. A represents how many units we are moving to the right or left. So on the x-axis, B represents how many units we're moving up and down, and that will be on the y-axis. When you get into three-dimensional space, it's a little bit different, and we'll talk about it when we get there. Now we have another axis, which is the z-axis, because we're three-dimensional, and I will show you how we look at that as we go through the lessons. Okay. All right. So we have a position vector and a displacement vector, which really, you guys know that any position vector can be a displacement vector because we can move it around. However, when we are drawing our vectors using components, then we know that we must start from 0, 0. So a position vector just means that it's starting at 0, 0. Okay, that's the origin. So we're starting at the origin. A displacement vector is just any vector that has been moved from this spot. Any vector u drawn on the Cartesian plane can be written in component form, so as an ordered pair, okay, in component form. So for example, this, we move A units to the right, we move B units up, and that's how we get our components A comma B. Okay? So if I want to find the length or the magnitude of that vector u, then all I need to do is use the Pythagorean theorem, right? We see that we have a right angle triangle form there, and I know how many components, how many units are there, excuse me, right? And we just use the Pythagorean theorem. So to find the magnitude of u, it's just the square root of a squared plus b squared, Pythagorean theorem, very simple math. So A and B, we say, are the components of vector u. That's how we make up vector u. So what you guys should be realizing is that A and B essentially are the slope, right? And so that's why it's the components of that vector. It's telling us the slope of the line of the vector, okay? Okay, example 1. Given the position vector W, which is -5, 2, so if I had to draw that as a position vector, then it would be 5 units to the left, 2 units up, right? That would be, the vector would start at 0, 0, and that's where it would end, at the point -5, 2. We want to find the magnitude of W, so we want to know how long it is, what's the size of vector W. And so we know that we have to use the Pythagorean theorem. Sorry, that's an arrow, guys. It's not coming out very nicely on my screen. And this is the vector in component form. So that represents vector W in component form. So we're looking for the magnitude. That's why we have those bars. And so we know that that is just the Pythagorean theorem. So 25 plus 4 will give us the square root of 29. So there is the magnitude of vector W. And now we want to know a unit vector W. Well, the unit vector W has to have the same slope. So we know that that -5, 2 can't change. It has to have the same slope. However, we don't want it to be root 29 units long. We only want it to have a length of 1. And so to find that unit vector W, I have to divide by the length. So I'm taking that vector W, which we know we can express in component form as -5, 2, and I'm dividing it by root 29. And now it's a unit vector. Okay, and that's unit vector W. Are there any questions? So once again, I found the magnitude of W. I found out how long that vector is. And then to find a unit vector, I want only a length of 1. And so I divide that unit vector, excuse me, that vector W by the length. Okay. And I used components here. I used the component form of the vector. On the xy plane, we define two unit or basis vectors, synonyms, okay, unit vectors or basis vectors, you could see both. I is 1, 0, so that's unit vector I, and if you notice, it runs along the x-axis. That's why it's 1, 0. J runs along the y-axis, and hence the components are 0, 1. Every position vector AB can be expressed in terms of the basis vectors I and J, okay, the unit vectors I and J. So here, if I have in component form A, B, well, I can just say now that it's A, which means how many units I'm moving on my x-axis, multiplied by 1, 0. That's what I is. And then here, I can just say that it's B multiplied by J. So however many units that I'm moving on the Y multiplied by 0, 1. Do you guys see that? So any vector in component form, I can now put in what's called standard basis form. And that means I'm using the unit vectors I and J, our basis vectors. Furthermore, every displacement vector is equivalent to a related position vector. Okay, so what does that mean? Here I have a position vector, OA. Here I have another position vector, OB. Here I have a displacement vector, AB. Well, I want to know what that AB vector was when it was at the origin. So many different ways to do that. I'm just going to show you an algebraic way to do it. So I know that OA plus AB, that's what we learned yesterday, will equal OB. Does everyone follow? My resultant vector will be OB. From here, I can rearrange. I can say that vector AB is equal to vector OB minus vector OA. Well, I have components for OB. And I have components for OA. And so now I just have to subtract the two vectors. And so I do 5 minus 2 is 3, and 4 minus 7 is -3. And I have now found my position vector, OC. Now, a simpler way to imagine this is, as I told you guys, here we have our rise and our run. If you find the rise and the run, it's always going to get you back to what the position was, right? It's going to give you that component form. So from here, and that's essentially what we did here, right? So I did 5 take away 2, which is 3. And I did 4 take away 7, which is -3. So I'm finding rise over run. Do you guys see that? Are there any questions? Okay. And so here we can see, I mean, it's clear, but you can see we're moving 3 units to the right and 3 units down to get here, to get this vector. Okay, so any vector AB in 2 space with a tail at ax1, y1 and a tip at x2, y2 has the following properties. So if you're looking now for vector AB, all you have to do, subtract the components, x2 minus x1, y2 minus y1, as you saw me do here. 5 minus 2, 4 minus 7. That's how I found AB. In standard basis form, you just take those components now and multiply them by unit vector I and unit vector J. The magnitude of that vector is just going to be those components, so x2 minus x1 squared plus y2 minus y1 squared. Again, it's just the Pythagorean theorem. Okay? When adding vectors in R2 already in component form, if A is equal to C comma D and vector B is equal to E comma F, then we want to add these two vectors together. I do C plus E, that's my component for X, and D plus F, that's my component for Y. Do you guys see that? Okay. Also, if vector A is equal to C comma D and B is equal to 3 comma A, then B is equal to 3 times C and 3 times D. Notice both your components get multiplied by 3. And this is why when we were talking yesterday about adding and adding vectors together, we said they have to have the same coefficient. And so this is why. Okay. Equality. Two algebraic vectors are equal if and only if their components are equal. So if you see that the components are equal, right away you know that the vectors are equal. If I tell you that two vectors are equal, then you can assume that their components are the same. That's what that's saying there. Again, it's that if and only if, it goes both ways. Any questions so far? Okay. Yeah, question?
Miss, I have a question. So like if you have two vectors, like for instance, like AB plus BC.
Yeah,
So we know like because the coefficient for both is 1, so we can obviously add them and we can say that's gonna be AC, like the result is gonna be
you
AC.
got it.
But how about if we write like AB plus CB? Is that like, does that make it change like to the answer or no?
Yes. So what this actually means is AB minus BC, which we know we can't do.
Hmm. But in the textbook, like we had like the same question like this in 6.2, I think in 6.2 homeworks, we had a question like this that was like negative, and then like we couldn't.
Let
I
me
don't
look.
know. Let me uh, bring it up.
Yeah. I don't have my textbook in front of me, but hold on. Let me see.
What was the question? Yeah, so like page
Which number?
291, question 5.
Question 5. Question 5. Hold on one second. Yeah, what does the question ask? Read it to me.
Each of the following vector expression can be simplified and written as a single vector.
Yep.
Write the single vector corresponding to each expression and illustrate your answer with a sketch. So
Okay, so
it's
read
like,
it to me.
yeah, so it's like number A is like a vector PQ minus RQ and then
Yep.
plus RS. Vector R.
Okay, so ready? So here, look here. Do you see how it's minus?
Yes.
We can now change that to be addition, and that works. When we're changing this to be now positive QR, it's okay because we're adding. What we can't do is subtract, but because it started off as a negative, now we're making it positive, it's okay. So this is now PR plus RS, which will be PS.
So you can change it to positive if it's negative. Like you can
Yeah,
change it. You can
yeah,
change
because look,
the.
so we have a vector that's going this way, right? So let's say that this is negative RQ. Well, so if it's going this way now, then we know it's QR.
Mhm.
Do you see that?
Okay, I see. Okay. So there will, okay. Okay, how about number B? Like can we do number B as well?
Yeah, you got to read it to me. Hold on, just give me 1 second. Uh-oh, hold on 1 second, guys.
Sure.
Hold on. Sorry, guys. I had to get my kids set up. Hold on, let me just close the door and let me get back to this.
Wait, miss, for the vectors on the top right, shouldn't they be in the same direction?
Okay, sorry, say that again?
Are the vectors in the top right, shouldn't they be in the same direction?
Yes, they should. Thank you. Here, I meant to do that.
Okay.
Yeah,
Thanks.
do you see that? Yeah, thank you. Okay, next example. You had another example for me?
Miss, I think I got the answer for this one, but if you want, I
Oh.
can just do it.
That's okay. No, that's okay. If you got it, then let's keep moving.
Okay.
Hold on. Where do we leave off? Okay. Okay, example 2. So given vector u is equal to 3, 1, and vector v is -5, 2, find vector w equals 2 times vector u plus 3 times vector v in both component form and standard basis form. So we're going to start with component form. So here I want to find vector w. I know the components of u, and I know the components of v. So you guys tell me, what am I going to do here? What did we see? I have to do
Multiply
what?
into-
Yep, multiply into both. Yes? And now we're adding the two vectors, so just add the two components. So at 6 minus 15 and 2 plus 6. Sorry, guys, I'm just going to put you on a quick hold and I'll be right back. Just give me 1 sec. Sorry, guys. I had to go and get my little guy set up. I apologize. This is not easy to work with them at home with me. Okay, so 6 minus 15 is what we're going to do here. And we're going to do 2 plus 6. That's component form. So now if I want to write this in standard basis form, I know that I just have to multiply by I and by j. Remember, guys, I is 1, 0, and j is 0, 1. And these are hats on the I and the j. Okay, not arrows, there's hats signifying that they are unit vectors. So this is component form. And this is standard basis form. Okay. All right. Given 3 parallelogram vertices in the xy plane, A 1, 1, B 2, 5, and C 7, 5, how many possibilities exist for the fourth vertex D? Okay, so let's draw what we have. Let's see this visually. So there's A, B is 2, 5. So there's B, C is 7, 5. And now we want to see where D could be. So it all depends on how I connect my vectors here. The first, and I think to me the most obvious, would be to do this. And so now my other vector, or excuse me, my other point would have to go somewhere here. And it has to, or somewhere here rather, it has to have the same slope. It has to be parallel. So here I can notice that I can find the slope, and whatever the slope is there, I just copy it over here, which happens to be over 1. So I'm going back 1, and we can see that it's on the same line. So that's one possibility for D. What's another possibility for B? What do you guys think? Let me draw them again. Where else could I draw D? Is there another possibility for D? No, no one has any ideas? Well, what about, oh, sorry, I drew the wrong one. My C is 7,5. So what do you guys think? What's another possibility for D? Do I have to connect A and B?
8,9.
Good. I can connect this way. Yes? And then again, I know that it has to be parallel. I need parallel lines, and so I use the slope to figure out my next point, which happens to be 8,9. Good. Two possibilities. Are there any others? What were my points here? 2,5. 1,1. 7,5. Okay, what do you guys think? What's another possibility? No one sees anything else? Well, what about if this time I connect B and C? What about if I do this? And I do this. Now, do you guys see it? So
Yeah.
what's my next coordinate? Yeah, what would it be? Anyone? Okay, well, we know that it has to be the same like
-4,
this.
1.
Yeah, so 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, and I'm just one off. And there you go. So 3 different possibilities for vertex D, okay? Now it says, use vectors to find the point of A comma B if it lies in quadrant 2. So the one that shows that D lies in quadrant 2 is my third example. And so they specifically want us to find the components of this. Now it's very easy to find by just looking at it, right? I can see it very clearly, but we want to show it algebraically. And so what we're going to do is we're going to use the addition and subtraction of vectors. Okay, so what I can see here is I can see that vector AC is equal to vector DB. I know that vector AC is equal to the components of C minus the components of A. So I found now the components for AC. Well, I need DB to have the same components. It has to be the same. And I know that D, I don't know D, excuse me, it's X comma Y, but I know B. I know that B is equal to 2 comma 5. And so I use subtraction now. Right, I'm doing B minus D in order to find 6 comma 4. And so from here I can see that 2 minus X has to equal 6. And 5 minus Y has to equal 4. And now it's very easy to solve for X and Y. So we can see that X is equal to -4. And we can see that Y is equal to 1. And so this is how you would show it algebraically. I know that you guys can draw me a picture and just find it, but I need to see all this work. Okay? Are there any questions? No? So again, guys, when you're looking for vectors between 2 points, we're subtracting the second vector from the first in order to get the components of that vector. How would I write this vector in standard basis form? Does anyone know? How would I write this vector in standard basis form?
-4I plus J, unit
Good.
vector.
Good. Ah, excuse me. Ha ha ha. What's the problem with the question I asked? Is D a vector? D is a point. So let me try that again. Let's write DB as in standard basis form. That's a better question. So if I had to write DB in standard basis form, it would be 6I plus 4J. That makes more sense. Cool? Good. If I wrote this here in standard basis form, now I'm talking about the position vector OD, which brings me to that coordinate. Yes, I would be talking about this. Do you guys see that? Okay. Alrighty, so guys, that's it for this section. The homework, why is it not here? Hold on, give me a sec. There it is. So your homework is page 324, numbers 1 to 16. Do you guys want to take a little break or do you want to go straight to 6, 7? It's up to you. Is anyone with me?
Break?
You guys want to go straight to 6, 7 or you want to take a break?
Is it a break?
Sorry?
Break?
Yeah, sure. How long of a break?
5-10 minutes.
Sure. Okay, so let's come back at 1:15. At 1:15, we'll do the second, we'll do 6.7, finishing off chapter 6, okay? Okay, guys, so we'll reconvene at 1:15.